So, good morning students. In the previous video session, we have discussed about the surface tension and the surface energy. And today we are going to discuss about the angle of contact. Angle of contact means, suppose if you are taking a water in a filler or something and we are just putting it down, we can see that the water drop becomes circular. We can see that the curved surface of the above this water surface. The same thing, if you are taking a plate or if you are taking a slide, just dipping inside the water. When we are taking this plate, after dipping the water, outside will be take, we can see that there will be some liquid on the surface. The same manner, if you are dipping this plate inside the mercury, that time also you can feel that some mercury is on this surface, but it is depressed. So, while we dip this plate inside the liquid of mercury, the liquid will form like this. You can see this diagram. Suppose you are dipping the solid inside the water, there will be some liquid at this surface. So there will be three surfaces you can divide. And this is what we can tell. Solid air, TSA. Surface tension due to the surface of solid and the air, and TLA. This is what air liquid interface. So surface tension due to what? The liquid air interface, and this is TSL. We can tell surface tension due to the layer, so solid and liquid. So in between these two layers, you see here solid, liquid, air. In between these two layers, we can see a line tangent to this liquid. So the line tangent to this solid liquid surface, we can tell that is, so there is an angle forming between this liquid and this air surface. Okay, you can see this diagram. There is a line tangent to this liquid and perpendicular to this solid. So there is an angle forming between these two surfaces. This angle we are saying angle of contact. So you can see the definition here. Angle between the tangent to the liquid surface inside the liquid is known as angle of contact between the solid and the liquid. You see, there is an angle between the inside this liquid. This is a line tangent to this liquid. So there is an angle forming between this liquid and this tangent line. So this angle, we are saying angle of contact, and this angle of contact is between the solid and the liquid interface. So this is what we are saying angle of contact. So again you see, there is an angle forming between this liquid and to this line tangent. Now this angle we are saying angle of contact between these two interface, solid and the liquid interface. Now you see, we can write the equation TSA is equal to TLA cos theta. Here there is an angle, so this is what we are saying TLA cos theta plus TSL. Surface tension due to the surface, solid and air, liquid and air, solid and liquid. Now we can find out the angle of contact theta by interchanging this equation, we can write this equation TLA cos theta plus TSL equal to TSA. Rearrange this equation and write TLA cos theta equal to TSA minus TSL. I have taken this TL this side. So we will get a cos theta equal to TSA minus TSL by T. So TSA minus TSL by TLA. So this is the equation we are getting. Cos theta is equal to TSA minus TSL by TLA. So by using this equation we can find out the angle of contact. Now you see there are three cases. First case is TSA is greater than TSL and TSA minus TSL is greater than 0. It means suppose assume that you got a value, the angle between these two surfaces, solid and air surface, you got 30 degree, and the angle between this solid liquid interface you got some 15 degree. Now when we substitute this 30, TSA means 30 minus TSL. So 30 minus 15 is equal to what we will get now? 15 degree. It is greater than 0. So this 15 degree means it is greater than what now? Greater than 0. So what we will get means we will get the theta value positive. Cos theta is positive. So you see here positive 15. It is what? So this is what first case. TSA is greater than TSL and TSA minus TSL is greater than 0. So the angle between the solid air interface is, we can keep it as 30 degree, and the angle between the solid liquid interface we got is 15 degree. If we substitute this 13 minus 15 here, we will get what? Positive 15, which is greater than 0, and that is what we can tell that cos theta is positive. Now the second case is TSA is less than TSL and TSA minus TSL is less than 0. It means it is this theta value we will get an obtuse angle. Also what we will get means the theta value we will get a minus value, negative value. So listen here, if we are substituting the same value but here surface is changed, you see TSA, the angle between the solid air interface you got 15 degree. The angle between the solid and liquid you got 30 degree. So when we substitute this 15 minus 13 is equal to minus 15, you will get so we are getting the theta value is negative. So that is what cos theta is, negative we are getting. So this is just for substitution I gave. So the second case, TSA is less than TSL. So the angle between solid air interface, assume that we got 15 degree, and the angle between solid liquid interface we got 13 degree. When we substitute this 15 and 13 in this equation, TSA minus TSL, so 15 minus 13 degree, so we are getting minus 15 degree. That is what the second case the angle of contact cos theta is negative. So here interface also given. For the first case water plastic interface, and the second case water leaf interface, and the third case if TSA is greater than TLA plus TSL, then TSA is equal to TLA plus TSL. Then what will happen means the state will be equilibrium, the water, the liquid which will be distributed everywhere, or you can tell that this liquid drop is spread over everywhere. That is what the third case. So this is what about the angle of contact. Now the next thing is, we know that we all have the experience of playing with the bubbles. So bubbles means we know that inside there will be some space, and outside also there will be air interface. So if you are taking a liquid drop also, you can see that inside some air liquid interface is there, and outside also some air liquid interface is there. So earlier we have learned about the surface tension, and you have learned that if any free surface is in contact with the liquid, what will happen? That part the liquid drop will be curved. So when it is curved, it is having some pressure inside as well as outside. There will be some pressure inside and outside, so there will be a difference pressure on this liquid drop. So now we can find out this excess pressure. Now we can find out this excess pressure. For that, first one, excess pressure inside a bubble and a liquid drop. So what will happen to this excess pressure inside a bubble or a liquid drop? If you are taking a small bubbles and a liquid drop, what we know that it will be spherical in shape. Also, you can see that why this liquid drop or this soap bubble you can see in spherical shape surface, because of its surface tension. Because of the surface tension, this liquid drop or the bubbles becomes what? Spherical. And you know why this is happening means, also there will be a pressure difference inside and outside. So when we are taking these bubbles or the liquid drop, inside there is some pressure which is acting, as well as there will be some pressure acting outside. So there will be a excess pressure between these two, inside pressure and the outside pressure. That we can find out. First one is excess of pressure inside a air bubble in a liquid. So excess of pressure inside air bubble in a liquid. You can see the diagram. Here there is a rim, and which is a circular shape. We know the distance of this rim is 2 pi r. And here there is a inside pressure which is acting inside, as well as in this cross sectional area there is some outside pressure also acting. Now we can find out. For that we are considering an air bubble of radius r and its surface tension T. Now we can find out the excess pressure. We know that P2 minus P1 is delta P. there is a change in pressure inside and outside. P1, P2 minus P1, we can write what? Delta P. Now there are some forces, this pressure producing inside and as well as outside, it is due to the force acting on the surface tension. So because of the force, there is a pressure producing here. There is an inward force acting, outward force acting. It is a reason why there is a pressure produced inside as well as outside. So that pressure, excess pressure, inside we have to find out. If we need to find out this inside pressure, we have to write first Ft about the forces. Force which is acting around this rim. That is what we can write 2 pi r, and on this surface tension T, 2 pi r T. 2 pi r is this length, and the force due to outside pressure P1 we can write pi P1 into pi r square. P1 into pi r square. We know this force acting outside pressure, force due to outside pressure. So here outside some pressure is there, that outside pressure is acting on this cross sectional area. Area we know, area means what? Pi r square. So force acting on this cross sectional area, that's what we are taking this, what? Pi r square. So Fp1 you can write P1 into pi r square. So the force Fp2 equal to P2 into pi r square. Now you need to find out this pressure, excess pressure. So inside pressure Fp2 is equal to Ft plus Fp1. This is what this is how we can find out the excess pressure inside. Fp2 is equal to Ft plus Pt. This one is equal to these two. We have to add. So P2 pi r square is equal to Ft is 2 pi RT. Now plus P1 pi r square. Now here take this tab P1 pi r square this side. So what we will get means P2 pi r square minus P1 pi r square is equal to 2 pi r t. From here pi r square, here pi r square. So pi r square take it commonly outside. So P2 minus P1 into pi r square equal to 2 pi RT. Now here pi cancel, r cancel. So what is remaining? P2 minus P1 equal to into r equal to 2t. So P2 minus P1 equal to 2t by r. So this is what is this P2 minus P1? P2 minus P1 means delta P, the excess pressure, 2t by r. This is what the excess pressure inside a air bubble in a liquid, 2t by r. Now the second thing, we can find out the excess pressure inside a soap bubble. Excess of pressure inside a soap bubble. Soap bubble. So excess of pressure inside a soap bubble. Here also, first we have found the excess of pressure inside a liquid air bubble in a liquid. For that we are taking the forces acting on that liquid. First one, the forces tangent to that rim. So 2 pi r t we have taken, and inside pressure, outside pressure Fp on we have taken P on pi r square, and inside pressure P2 is equal to P2 pi r square. Now we have to find out the excess pressure, so that we can take the pressure inside is equal to Ft plus Fp on. That's what we are substituting this. Fp2 means P2 pi r square, and Ft means 2 pi r t, then Fp or P on pi r square. After substitution, take this P on term this side, so P2 pi r square minus P on pi r square is equal to 2 pi r2 will get from this. Pi r square is common here and here, so take the pi r square outside. While taking this pi r square outside, we'll get P2 minus P1 into pi r square is equal to 2 pi r t. Now you have to cancel the pi and r. So cancel this pi here, and one r from here and another r from here. So the remaining things we will get P2 minus P1 into r is equal to tt. While taking this r another side, so P2 minus P1 is equal to 2t by r. So P2 minus P1 means what? The excess pressure, the change in pressure, delta P. So the delta P is equal to 2t by r. Now the next thing is the excess pressure inside a soap bubble. So now we are finding the excess pressure inside a soap bubble. Okay, so before finding this, now also the same thing, Ft. Now we are taking a soap bubble. Soap bubble means you know that inside surface, inside one air, liquid interface will be there. Outside also same thing will be there. So inside two rims, the total rims we can take is 2 pi RT into 2 is equal to 4 pi RT. And the outside pressure is same P on pi r square. Inside pressure is same P2 pi r square. So same calculation we can do here, 4 pi RT. So here what will come? 4 pi RT. So here also 4. Here 4. So for this is what for soap bubble we will get delta P is equal to 4T by R. So listen here, the same thing here. Air bubble, soap bubble means you can see the diagram in the page number 78. Soap bubble, there will be two surface, inside one spherical surface and inside air liquid interface will be there. Outside also the same thing will be there. So the forces due to force acting on that tangent, or you can tell the rim of length is what? 2 pi RT, and there is two surface, so into 2 you have to take, so 4 pi RT we will get, and outside pressure P1 is P on pi r square, inside pressure P2 pi r square, and the same thing we are doing what? To find the excess pressure. So Fp2 is equal to Ft plus Fp1. Now P2 substitute here, P2 pi r square, here what? Here 4 pi RT, and the next step by P on pi r square we are taking this side, so P2 pi r square minus P on pi r square is equal to 4 pi RT. From here pi r square take it outside commonly, so cancel this pi, then r and r, so remaining what? P2 minus P1 into r is equal to 4T you will get. Now the change in pressure, excess pressure is delta P is equal to 4T by R. And the next thing is we have to find out the excess pressure inside the liquid drop. Excess pressure inside a liquid drop. Liquid drop. You can see that the diagram inside one liquid drop of radius r and whose surface tension acting on it is T, and you can see that the diagram inside there is a pressure acting, and as well as same the outside pressure also acting. So inside pressure acting is equal to outside pressure, the same thing, F T. Around that rim is acting 2 pi RT, and outside pressure Fp1 is equal to P1 pi R square. F inside pressure Fp2 is equal to P2 pi R square. Now we need to find out the excess pressure inside. For that you can write Fp2 is equal to Ft plus Fp1. You can see in that diagram, inside one pressure is acting, and outside on that rim, that circular rim, there are some forces acting. That is what Fp2 is equal to Ft plus Fp1. Now the same step. Fp2 means what now? P2 pi r square. Ft means 2 pi rt. Plus Fp1 means T1 pi r square. Now after taking, now we have to take this term this side. So P2 pi r square minus P1 pi r square is equal to 2 pi rt. Take this pi r square outside. So P2 minus P1 inside bracket 2 pi rt. Cancel this. 1 pi. So P2 minus P1 is delta P is equal to Tt by R. Again the same pressure. This is how we can find out the excess pressure inside the liquid drop, excess pressure inside a soap bubble, and the excess pressure inside a bubble and a liquid drop. Now the next thing is about the capillarity. Capillarity means, inside the thermometer and all, you can see there is a small thread like thing. It is very thin, like its width is like our hair and all. That only we are saying capillarity. And this word derived from a Latin word capilla. Capilla means hair. So if you are using a hair tube, very small tube, capillarity. So very thin tube we are using means the rising level will be higher. That is what about capillarity. So that is what in the thermometer and all they use very thin capillary tube, so that very fast, easily they can find out the temperatures. When the temperature increased inside the capillary tube, the mercury is rising. So here, suppose like this on water surface, if you are keeping a capillary tube inside like this, a capillary tube which is both end opened, and if you are keeping this capillary tube inside the water surface, so what happened means you can see the liquid level inside the capillary tube rise more than the water level in the surface. Also this angle of contact, here you can see there is an angle of contact which is less than angle of contact which is what? Here you can see which is greater than. In some liquid the angle of contact is greater than 90 degree, so that what will happen, what we can till means capillary, that is what capillary rise. And some liquid, suppose if the same thing you are dealing with a mercury, so you can see that part is depressed. And this angle of contact which is less than 90 degree, which is less than 90 degree, so you will get an acute angle. If the angle of contact is less than 90 degree, so that we can take it is capillary rise. capillary fall. So two things, the angle of contact which is less than 90 degree, that is what capillary, it suffer capillary fall. The angle of contact inside the tube which is greater than 90 degree, that is what capillary rise. And this capillary rise or fall, maybe the liquid inside the capillary tube will rise or the liquid inside the capillary tube falls. Both happening, it depends upon the narrower. How much narrower the tube, the rise or fall will change. So, this is what about the capillary tube. And there are some practical application by using this capillarity. You know, the first thing is capillarity application. Old people use the earthen lamp. So old people use this earthen lamp. Their oil rises in the cotton. It is due to this application, practical application, capillarity. Also the second application is we are using the blotting paper to absorb the ink. If ink drop is fall on somewhere, some surface, we are using the blotting paper to take that ink. That is also one of the application of capillarity. And the next application is, you know, in our eye always some fluid will be there. Sometimes we can see our eye is filled with fluid. After sometimes we can see that it is drained. Actually, why this is happening? How it drains? It is one of the application of this capillarity. And the last application is, we prefer cotton dresses during summer season. Why we prefer cotton dresses in summer season? When we compare this cotton dresses with other dress, very small pores you can see in between in our cotton dresses. That's what it is. It is absorbing the sweat and we are not feeling hot very much. So this is also one of the application of capillarity. So for application, first one is the earthen lamp, which is used in the olden people, used by the olden people. In our house also, old house, they use this earthen lamp. That is one of the application of capillarity. And the second application is absorbing the ink by using the blotting paper. And the third one is capillary rise. Tear fluid from our eye, you can see it drains fast. That is also one of the application of capillarity. And the last one is the people use the cotton dresses during summer season. That is also one of the application of capillarity. So all of you revise this part of this angle of contact. It is one of the important 3-mark question. So go through that. Thank you all. Bye bye.